Welcome back. In this video, you'll learn how to find the arc length of polar curves. Let's get to it. Alright, so previously in Calculus 2, you have seen how to calculate the arc length of curves within the rectangular coordinate system. And those curves have been represented by rectangular equations, or more recently, with parametric equations. However, we can also calculate the arc length for polar curves within the polar coordinate system. And in order to see how to calculate the arc length of polar curves, we need to quickly revisit how we calculated the arc length of curves in the rectangular coordinate system, specifically in parametric form. And so if you take a look at this graph here you can see that we are working within the rectangular coordinate system. We have our x-axis and our y-axis, and we have a curve here represented by two parametric equations. And so this curve would be a parametric curve. It's represented by x equals f of t and y equals g of t. So t is our parameter. All right, and so for this parametric curve, we can calculate the arc length of a particular section of that curve between two values of t by using a particular formula. And that formula looks like this. The arc length is equal to the integral from t sub 1 to t sub 2, those two values of t that the arc length lies between, of the square root of dx dt squared plus dy dt squared dt, where dx dt is the derivative of the parametric equation for x with respect to t, and dy dt is the derivative of your parametric equation for y with respect to t. All right, in both cases, those derivatives are with respect to the parameter. All right, and so you've seen this before. This is how you calculate the arc length of a curve when it's represented by parametric equations. But the reason that we revisited calculating arc length in parametric form is that it's going to help us determine how to calculate arc length in the polar coordinate system for polar curves. And so as you can see right here, I have a polar graph within the polar coordinate system. Our curve is represented by this polar equation, r equals f of theta. And for this curve, we want to calculate the arc length between two angles of theta. And so the question is, how can we calculate this arc length between those two angles of theta for this polar curve? Well, what we can do is make use of this formula right here, right? This is how you calculate arc length for a curve represented by parametric equations. And remember, we can actually represent a polar curve or a polar equation with a pair of parametric equations. What we can do is use the following two formulas of x equals r times cosine theta and y equals r times sine theta. These are two equations that we use to convert between polar coordinates or polar equations and rectangular coordinates or rectangular equations, right? These two equations relate x and y to r and theta. What we can do with these two equations is replace r with what it's equal to, which is a function in terms of theta. And if we do that, we'll have x is equal to f of theta times cosine theta, and y is equal to f of theta times sine theta. And now what we have are a pair of parametric equations that represent this polar curve. We have a parametric equation for x in terms of a parameter theta, and we have a parametric equation for y that is also in terms of that parameter theta. So what we can do is use this pair of parametric equations to set up a definite integral that will represent the arc length of a polar curve. All we have to do is take the derivative of each of our parametric equations and plug them into this formula, right? To calculate the arc length for a curve represented by parametric equations, you integrate the square root of dx dt squared plus dy dt squared. Now in this case, this formula is assuming that your parameter is t, but if we switch the parameter to theta, then it becomes a little bit more obvious how we can use this formula with these two parametric equations to calculate the arc length of a polar curve. And so let's work on that. Let's first work on rewriting this formula to be in terms of a parameter theta, and then we'll use it with these two parametric equations to come up with a formula to calculate arc length in polar form. All right, so here's our formula for arc length in parametric form. Let's rewrite this so that our parameter is now theta. The arc length will be equal to the integral from theta sub 1 to theta sub 2. In other words, we're integrating between two values of theta, which if you look at our graph, we have those two angles labeled with alpha and beta. the lower angle is alpha and the upper angle is beta. So instead of writing theta sub 1 and theta sub 2, let's just use alpha and beta. So I'm going to erase those. Let's just replace theta sub 1 and theta sub 2 with alpha and beta. All right. And then inside the integral, we will have the square root of dx d theta squared plus dy d theta squared. All right. And then we're going to be integrating with respect to theta. So we will have dx d theta squared plus dy d theta squared times d theta. All right, so now we still have an integral that is going to calculate the arc length in parametric form, but now we're using theta, which now matches our two parametric equations that represent our polar curve. So now what we want to do is find dx d theta and dy d theta and plug them into this formula. We need to take the derivative of our parametric equation for x with respect to theta and take the derivative of our parametric equation for y with respect to theta. All right, so let's find dx d theta first. Dx d theta is equal to the derivative of f of theta times cosine theta. Now these are two functions of theta being multiplied by each other, so in order to take the derivative of that, we will need to use the product rule. We have a product of two functions. So if you don't quite remember the product rule, I'll have it up here on the screen for you to reference. But here's how it works. We take the first function and multiply it by the derivative of the second function. So we'll have f of theta times the derivative of cosine, which is negative sine. So we'll have negative sine theta. And then we'll add that to the second function times the derivative of the first. So we'll have cosine theta times the derivative of f of theta, which is f prime of theta. All right, and now I'm going to make this look a little bit nicer. I'm going to reorder our terms and reorder the multiplication here. So dx d theta will look like this. I'm going to have f prime of theta times cosine theta minus f of theta times sine theta. All right, so f of theta times negative sine theta is negative f of theta times sine theta. And then I reorder these terms, so that's the last term. And so this term is now out front. And I just reordered the multiplication so that we have f prime of theta first. All right, this is just how I want to have dx d theta written so that it's a little bit easier for us later on when we go to simplify this integral after plugging in dx d theta and dy d theta. All right, but we're not quite there yet. We only have dx d theta. We still need to find dy d theta. So let's take the derivative of y with respect to theta. Dy d theta will be equal to the derivative of f of theta times sine theta. And once again, we have a product of two functions defined with theta, so we will need to use the product rule. We'll start with the first function times the derivative of the second. So we'll have f of theta times the derivative of sine, which is cosine. So we'll have cosine theta, and then we'll add that to the second function times the derivative of the first. So we'll have sine theta times f prime of theta. All right, now if I reorder these terms, just like I did with dx d theta, I'm going to make this term with f prime of theta first, and then we'll add that to this second term. And I'm also going to reorder the multiplication of sine theta and f prime of theta. So dy d theta will be equal to f prime of theta times sine theta plus f of theta times cosine theta. All right, so that's what dy d theta will be equal to. So now that we have both dx d theta and dy d theta, we can plug their expressions into this formula and then simplify to find a formula that will calculate arc length of polar curves. If we do that, if we plug in dx d theta and dy d theta into this integral, here's what we're going to have. The arc length is going to be equal to the integral from alpha to beta of the square root of dx d theta squared. So we're going to have this whole expression squared. So let's write that in there. We're going to have f prime of theta times cosine theta minus f of theta times sine theta squared. And we're going to add that to dy d theta squared. So let's make this square root bigger. And then we will have dy d theta squared. So let's put this expression right here. We'll have f prime of theta times sine theta plus f of theta times cosine theta squared, and then don't forget d theta. All right, and so now we have dx d theta squared plus dy d theta squared d theta. Now this looks pretty complicated at the moment, and it is going to get a little bit more complicated because we're going to square each of these quantities. But after we square them, there's going to be a lot of nice simplifying that we can do that will result in a very nice and simplified formula. All right, and so let's work on simplifying this definite integral, and we will start by squaring each of these quantities. So here's what we'll have. We'll have the integral from alpha to beta, and then we have the square root of these two quantities squared. Now I'm going to wait to draw in the square root later. I'll do that after we write out all of our terms. All right, so let's just focus on expanding this quantity squared and this quantity squared. And so let's start by squaring this quantity first. And to do that quickly, I'm going to use a little trick. We need to square the first term. Then we'll add that to these two terms multiplied together, but then multiplied by 2. And then we'll add that to the last term squared. So we'll have f prime of theta squared times cosine squared theta. That's this first term squared. Then we're going to add that to these two terms multiplied together and then multiplied by 2. So if we multiply these two terms together, we're going to have all 4 of these parts multiplied into one term, but because we have a negative f of theta sine theta, that term will be negative. All right, so we're going to have minus 2, remember we need to multiply it by 2, f prime of theta times f of theta times cosine theta times sine theta. All right, so we have all 4 parts here, and we're multiplying it by 2. F prime of theta is here, f of theta is here, cosine theta is here, and sine theta is there. And of course, we also have the negative sign. All right, and then finally, we'll add that to the last term squared. And if you square this last term, we will have f of theta squared times sine squared theta. All right, so those are the 3 terms that result from squaring this quantity. Now let's work on squaring this quantity. We'll have plus this first term squared. So we'll have f prime of theta squared times sine squared theta. And then we will add that to these two terms multiplied together, but then multiplied by 2. So we'll have 2 times f prime of theta times f of theta times cosine theta times sine theta. All right, all 4 parts are within that term, and then we're multiplying it by 2. F prime of theta is here, f of theta is here, cosine theta is there, and sine theta is there. All right, and then finally, we need to add that to the last term squared. And so if we square f of theta times cosine theta, we will have f of theta squared times cosine squared theta. All right, and all of that is underneath a square root. So let me just draw that in here. And then don't forget d theta. All right, so there's all the terms that result from squaring these two quantities. Now what we want to do is work on simplifying all of these terms. And the first thing that I see is that we have 2 terms that are going to cancel out. We have negative 2 times f prime of theta times f of theta times cosine theta times sine theta, and then we have positive 2 times f prime of theta times f of theta times cosine theta times sine theta. They are the exact same terms, except one is positive and one is negative. So what we can do is cross them out. We don't need those 2 terms because they will cancel out with each other. So here's what we're left with. This will be equal to the integral from alpha to beta. And once again, I'll draw in the square root at the end, so don't think that I'm forgetting it here. We'll have f prime of theta squared times cosine squared theta. And then I'm going to come back to this term, because what I want to write next is the other term that has f prime of theta squared within it. That's going to be important for our next step. So after rewriting this first term, I'm now going to rewrite this term. We'll have plus f prime of theta squared times sine squared theta. All right, and then we'll add that to this term, and then we'll add our last term. So now we have f of theta squared times sine squared theta, and then plus f of theta squared times cosine squared theta. All right, and all of that is still underneath a square root, and then we have d theta. Okay, and so now with our remaining 4 terms, what I want you to notice is that the first 2 here that I have written both have a common factor of f prime of theta squared, right? We have f prime of theta squared times cosine squared theta and f prime of theta squared times sine squared theta. And then for these 2 terms, they both have a common factor of f of theta squared. We have f of theta squared times sine squared theta and f of theta squared times cosine squared theta. And so what we can do is pull out those common factors from each of those pairings, and that will help us see how to simplify this further. So let's do that. If we pull f prime of theta squared out of these first two terms, this will be equal to the integral from alpha to beta of f prime of theta squared times cosine squared theta plus sine squared theta. And then we'll add that to these two terms, but now we're going to pull out f of theta squared, and so we'll have f of theta squared times sine squared theta plus cosine squared theta. And so that's all still under a square root, and then don't forget d theta. All right, so now we pulled f prime of theta squared out of these two terms, so if we pull it out, we're just left with cosine squared theta and sine squared theta, and we pulled f of theta squared out of these two terms, so now we're just left with sine squared theta and cosine squared theta. All right, and so now we're almost done. We're almost done simplifying this integral to represent the arc length in polar form, because all we have to recognize now is that cosine squared theta plus sine squared theta, this quantity and this quantity, are both equal to 1, right? We know that from the Pythagorean identity for sine and cosine, that 1 is equal to sine squared theta plus cosine squared theta. So it doesn't matter what order you add cosine squared theta or sine squared theta, whether you have cosine squared theta plus sine squared theta or sine squared theta plus cosine squared theta, both of those quantities are just equal to 1. We're multiplying f prime of theta squared times 1 and f of theta squared times 1. So we don't need to rewrite these quantities. They just become 1, right? And what we'll be left with is that this is equal to the integral from alpha to beta of the square root, and then I'm going to reorder these terms. I'm going to write this one first and then this one. We're just going to have f of theta squared because we're multiplying it by 1. So we'll write that in. We're going to have f of theta squared, and we'll add that to this term, which is just f prime of theta squared times 1. So we're just going to have f prime of theta squared. So I'll write f prime of theta squared d theta. And this right here represents the arc length of a polar curve. We just integrate between the two angles of theta that we want to know the arc length between of the square root of f of theta squared, and f of theta is just whatever your polar equation is, right? R equals f of theta. And then you're adding that to f prime of theta squared, which is just the derivative of your polar equation that represents your polar curve. So another way that we could write this is to say that this is equal to the integral from alpha to beta of the square root of r squared plus dr d theta squared times d theta, right? F of theta is the same as r, so we can write r squared, and so that means that the derivative of f of theta, or the derivative of r, would be dr d theta, the derivative of r with respect to theta. And so this right here is the formula that represents the arc length in polar form. And so to summarize what we just found, the arc length of polar curves can be calculated using this definite integral, that the arc length is equal to the integral from alpha to beta, which are two angles of theta, of the square root of r squared plus dr d theta squared d theta. And of course, r is whatever your polar equation is that represents your polar curve, and dr d theta is just the derivative of r, the derivative of the equation that represents your polar curve. All right, and so now that we have this nice formula, let's use it in some example problems where we will calculate the arc length of polar curves. Okay, so here's our first example. We want to find the arc length of the curve represented by the polar equation on the given interval. And so we have r equals 8 as our polar equation, and we want to know the arc length between an angle of 0 and 2 pi. All right, so to calculate the arc length, we need to use that formula, that the arc length is equal to the integral from alpha to beta of the square root of r squared plus dr d theta squared times d theta. Now in this case, we can already see that r is equal to 8, so r is equal to 8, which means that dr d theta, the derivative of r with respect to theta, will be 0. 8 is just a constant, it's not being multiplied by theta, and so the derivative will just be the derivative of a constant, which is 0. So if we plug these two values into our formula and replace alpha and beta with these two angles of 0 and 2 pi, we can calculate the arc length. We will have that the arc length is equal to the integral from 0 to 2 pi of the square root of r squared, so we'll have 8 squared plus dr d theta squared, which will be 0 squared, and then d theta. All right, and so now we have a pretty simple integral here. 0 squared is 0, 8 squared is 64, so we have 64 plus 0, and the square root of 64 is 8. So this is just equal to the integral from 0 to 2 pi of 8 d theta. And we know that the integral of a constant like 8 is just going to be that constant times the variable of integration, which in this case is theta. So if we integrate, this is equal to 8 theta evaluated from 0 to 2 pi. All right, and so if we evaluate 8 theta at 2 pi and subtract the evaluation at 0, this is going to be equal to 8 times 2 pi minus 8 times 0, which is just going to be equal to 16 pi, right? 8 times 0 is 0, so we just have 8 times 2 times pi, which is 16 pi. And so 16 pi is the arc length of this curve, r equals 8, between these two angles of theta. In fact, if you're familiar with the graphs of your polar equations, then you probably know that r equals 8 just represents a circle centered at the origin with a radius of 8. And so to draw a quick sketch, if this is our polar coordinate system, this circle right here would represent the graph of r equals 8. If we say that this right here is a radius of 8 and this right here, this is our angle of 0 and then pi divided by 2. We just calculated the arc length of this curve from 0 to 2 pi, which in this case, all that is the measurement around this circle with a radius of 8, which is just the circumference of this circle, right? 16 pi, this arc length, is just the circumference of this circle. And so you can check your work here. We know that the circumference of a circle is equal to 2 times pi r, and so the radius of this circle is 8, and so you can very quickly see that that is equal to 2 pi times 8, which is equal to 16 pi. All right, so I thought I'd just point that out. The arc length that we calculated here was just the circumference around a circle. Okay, let's take a look at another example of calculating arc length of a polar curve. All right, so here's our next example. We want to find the arc length of the curve represented by the polar equation on the given interval. This time we have r equals 7 times sine theta, and we want to find the arc length between theta equals 0 and theta equals pi divided by 2. All right, so if you're familiar with the graph of your polar equations, in this case we're also working with a circle. 7 times sine theta represents a circle resting above the polar axis with a diameter of 7. So our polar curve would look like this if we said that this right here was a distance of 7 from the origin. So this circle has a diameter of 7, and we want to calculate the arc length of this circle from an angle of 0 to an angle of pi divided by 2. So that's from this angle of 0 to this angle of pi divided by 2. So the arc length that we're calculating will be half of the circumference of this circle. All right, so that's what we're finding in this case. But now let's actually find it. The arc length is equal to the integral from alpha to beta of the square root of r squared plus dr d theta squared times d theta. In this case, r is equal to 7 times sine theta. And so dr d theta, the derivative of r with respect to theta, will be equal to the derivative of 7 times sine theta. Now the derivative of sine is cosine, so we'll have 7 times cosine theta. All right, so now let's use these values to calculate the arc length. If we replace r and dr d theta with what they're equal to, and replace our bounds of integration with 0 and pi divided by 2, we will have that this is equal to the integral from 0 to pi divided by 2 of the square root of r squared, so we'll have 7 times sine theta squared plus dr d theta squared, so we'll have 7 times cosine theta squared d theta. All right, so now if we square both of these terms, this will be equal to the integral from 0 to pi divided by 2 of the square root of 49 times sine squared theta plus 49 times cosine squared theta d theta, right? 7 squared is 49, sine theta squared is sine squared theta, and cosine theta squared is cosine squared theta. All right, now if we work on simplifying this integral, notice that both of these terms underneath the square root have a common factor of 49 that we can pull out. So this will be equal to the integral from 0 to pi divided by 2 of the square root of 49 times sine squared theta plus cosine squared theta d theta. All right, but now, because of our Pythagorean identity for sine and cosine, we know that sine squared theta plus cosine squared theta is equal to 1. So we just have 49 times 1 underneath the square root, and 49 times 1 is 49. So we have the square root of 49, which we know to be 7. All right, so this quantity becomes 1. 49 times 1 is 49, and the square root of 49 is 7. So this is equal to the integral from 0 to pi divided by 2 of 7 d theta. All right, and then 7 is just a constant, so the integral of that will be 7 times theta. So this is equal to 7 theta evaluated from 0 to pi divided by 2. And so if we evaluate 7 theta at pi divided by 2 and subtract the evaluation at 0, this is equal to 7 times pi divided by 2 minus 7 times 0. But 7 times 0 is 0, so I'm just going to erase that. We're just subtracting 0, and so our final answer is 7 pi divided by 2. That is the arc length for this polar curve between these two angles of theta. Okay, let's take a look at one more example for this video. All right, so here's our last example. Once again, we want to find the arc length of the curve represented by the polar equation on the given interval. And we have r equals 1 plus cosine theta, and we want to calculate the arc length between theta equals 0 and theta equals 2 pi. All right, now if you're familiar with the graph of 1 plus cosine theta, that is actually a cardioid. And so a quick sketch of that will look like this. If this is our angle of 0, this is pi divided by 2, pi, and 3 pi divided by 2. The cardioid for 1 plus cosine theta will look something like this. All right, it's not a perfect drawing, but that is the shape that would result from graphing this polar equation. And so if we want to find the arc length from an angle of 0 to an angle of 2 pi, we are calculating the arc length around this entire cardioid, from an angle of 0 all the way to an angle of 2 pi. All right, so in order to calculate this arc length, we need to use our formula. The arc length will be equal to the integral from alpha to beta of the square root of r squared plus dr d theta squared times d theta. All right, now in this case, we know that r is equal to 1 plus cosine theta. So that means that dr d theta, the derivative of r with respect to theta, will be equal to the derivative of 1, which is 0, plus the derivative of cosine theta, and the derivative of cosine is a negative sign, so we'll have negative sine theta. All right, so now let's set up our definite integral. This will be equal to the integral from 0 to 2 pi. Those are our bounds of integration. And then we'll have the square root of r squared. So we'll have 1 plus cosine theta squared plus dr d theta squared. So we'll have negative sine theta squared times d theta. All right, so now what we want to do is square this quantity and square negative sine theta, and then work on simplifying the contents of this square root so that we can then integrate it. All right, so if we square 1 plus cosine theta, we need to use that little trick. We'll square the first term, then add that to these two terms multiplied together times 2, and then add that to the last term squared. So this will be equal to the integral from 0 to 2 pi of the square root of 1, that's going to be 1 squared, and we'll add that to 2 times these two terms multiplied together. 1 times cosine theta is just cosine theta, so we'll have 2 times cosine theta, and then we'll add that to this last term squared, which will be cosine squared theta. All right, and so then we'll add that to negative sine theta squared, which will be positive sine squared theta. All right, and then we have d theta. Now to simplify further, notice that something pretty nice happened here. We have cosine squared theta plus sine squared theta. We know that that is equal to 1 using that Pythagorean identity. So this is just going to become 1, but we're not multiplying it by anything, right? We are adding these two terms, so we're going to be adding 1. So what we have here is that this is equal to the integral from 0 to 2 pi of the square root of 1 plus 2 times cosine theta plus 1, and then that's multiplied by d theta, but we can combine these two ones. We'll have 2 plus 2 times cosine theta, and so that will give us this integral, the integral from 0 to 2 pi of the square root of 2 plus 2 times cosine theta d theta. All right, and so now let's see if we can simplify this integral any further. One thing that I see that we can do is pull out a common factor of 2 from both of these terms. And so if we do that, this will be equal to the integral from 0 to 2 pi of the square root of 2 times 1 plus cosine theta d theta. All right, now what we can do is take the square root of each of these parts individually. We'll have the square root of 2 and then the square root of 1 plus cosine theta. And then we can pull out that constant of the square root of 2 to the front of the integral. And that will look like this. We'll have the square root of 2 times the integral from 0 to 2 pi of the square root of 1 plus cosine theta d theta. Okay? And so now at this point, we've simplified as far as we can, at least upon first glance. But now we have a little bit of a problem. It's not entirely clear how we can integrate the square root of 1 plus cosine theta. This seems to be a bit of a tricky integral. And so whenever you get in a situation like this, where you have an integral, where you're dealing with trig functions, and you're not really sure how to proceed, you really don't know how to integrate what you're left with, you should try to see if you can think of some trigonometric identity that will help you simplify this further. Now in this case, we have 1 plus cosine theta. Whenever you see 1 plus cosine theta, you should think of one of your half angle identities. In particular, I'm referring to this identity, that cosine squared theta is equal to 1/2 times 1 plus cosine of 2 theta. Right? Now in this case, we don't have 1 plus cosine of 2 theta, we have 1 plus cosine of theta. So what we can do is just divide both of these angles on both sides of this equation by 2. So that will look like this. We'll have cosine squared of theta divided by 2 is equal to 1/2 times 1 plus cosine of theta. And now this more closely resembles what we have here. We just have to multiply both sides by 2 to remove this 1/2, and then we'll have 1 plus cosine theta. So if we do that, we'll have 2 times cosine squared of theta divided by 2 is equal to 1 plus cosine theta. So we can replace 1 plus cosine theta right here in our integral with 2 times cosine squared of theta divided by 2. Now the reason why that's helpful is because we can take the square root of cosine squared, right? That will help us simplify our integral further. So here's what we'll have. We can rewrite our integral like this. The arc length will be equal to the square root of 2 times the integral from 0 to 2 pi of the square root of 2 times cosine squared of theta divided by 2. And then we have d theta. All right, so we just replaced 1 plus cosine theta with 2 times cosine squared of theta divided by 2 by using this identity and just rewriting it a little bit to be in this form. All right, so these two integrals are equivalent, but now what we can do is take the square root of 2 times cosine squared of theta divided by 2. And so if we do that, this will be equal to the square root of 2 times the integral from 0 to 2 pi of the square root of 2 times cosine of theta divided by 2 d theta. Now, at this point, we need to be a little bit careful, because whenever you take the square root of a function, technically what that's equal to is the absolute value of that function. And so when we take the square root of cosine squared of theta divided by 2 here, we need to be careful and make sure that cosine of theta divided by 2, what we're saying is the square root of that, is positive between these two angles of theta. All right, and so if we were to look at the graph of cosine of theta divided by 2, it would look a little bit like this. Along the horizontal axis, I'll label pi and 2 pi, and then along the vertical axis, I'll label 1. The graph of cosine of theta divided by 2, or if you're treating the horizontal axis as being the x-axis and the vertical axis as being the y-axis, then cosine of x divided by 2 would look like this. We'll start here, pass through the x-axis at a value of pi, and then you're down to -1 along the y-axis at 2 pi. So cosine of theta divided by 2 is not positive for all values of theta between 0 and 2 pi. It's only positive for half of the values, from 0 to pi. And so that's going to lead to some problems later on when we actually go to solve this integral and evaluate at our bounds of integration. If you wanted to, you could go ahead and solve this integral as it stands, but if you were to use these bounds of integration from 0 to 2 pi, you're going to get an arc length of 0, which obviously doesn't make sense. The arc length of this cardioid is not going to be 0. It should be some value bigger than 0, and so we've got a little bit of a problem here, right? It seems like we can't just take the square root of cosine squared of theta divided by 2, but we can if we adjust our bounds of integration. Since we know that cosine of theta divided by 2 is positive between 0 and pi, we can change our bounds of integration to be from 0 to pi and then make use of symmetry. Because if you look at our graph here, this cardioid is symmetric about the polar axis. So what we can do is calculate the arc length from an angle of 0 to an angle of pi, and then just double that arc length, multiply it by 2. All right, and by doing that, we will then be integrating between 0 and pi, which would be values of theta for which cosine of theta divided by 2 is positive. All right, so here's how we're going to rewrite this integral. The arc length will be equal to 2 times the square root of 2 times the integral from 0 to pi of the square root of 2 times cosine of theta divided by 2 d theta. All right, so now instead of integrating from 0 to 2 pi, we're just integrating from 0 to pi, which accounts for half of the arc length, and so we need to double it, so I multiplied our integral by 2. All right, so now we can work on simplifying and then finally solving this integral to find our arc length. Okay, and so I'll start by pulling this square root of 2 to the outside of the integral. So we'll have the square root of 2 times the square root of 2, that's just going to be 2, and then we're multiplying that by 2. So 2 times the square root of 2 times the square root of 2 will be 4. So this is equal to 4 times the integral from 0 to pi of cosine of theta divided by 2 d theta. Now, in order to integrate cosine of theta divided by 2, we do need to use u substitution. We need to set u equal to this inside function of cosine and then rewrite our integral in terms of u. So let u equal theta divided by 2, which means that du d theta, the derivative of u with respect to theta, will be 1/2. And then if we multiply both sides by d theta, we'll have that du is equal to 1/2 times d theta. And then whatever du is equal to needs to be found within our integral, but I don't see 1/2 d theta, I just see d theta. So we need to multiply both sides by 2 to have 2 times du is equal to d theta, right? Multiplying both sides by 2 eliminates this 1/2 because 2 times 1/2 is 1. So now we can replace d theta with 2 times du. So now we can rewrite this integral in terms of u. We'll have that this is equal to 4 times the integral from theta equals 0 to theta equals pi of cosine u times 2 du. All right, we replace theta divided by 2 with u and d theta with 2 du. But now our bounds of integration are still in terms of theta, so let's rewrite those to be in terms of u so that we don't have to go back into terms of theta. We can just integrate and evaluate in terms of u. So what we'll do is plug these values of theta into what we set u equal to. And so when theta equals 0, we'll have 0 divided by 2. So u is going to be equal to 0. 0 divided by 2 is going to be 0. So if I change our lower bound, instead of theta equals 0, we will have u equals 0. And then for the upper bound, when theta equals pi, we'll have pi divided by 2 as our value of u. So the upper bound, instead of being theta equals pi, will be u equals pi divided by 2. Okay, so now u substitution is done. We can now integrate and then evaluate in terms of u. So the first thing I'll do is pull this 2 out to the front. We'll have 2 times 4, which is 8. So this is equal to 8 times the integral of cosine u, and the integral of cosine is sine. So we'll have sine u evaluated from 0 to pi divided by 2. And so now let's evaluate sine at pi divided by 2 and subtract the evaluation at 0. So if we do that, this will be equal to 8 times sine of pi divided by 2 minus sine of 0. Sine of pi divided by 2 is equal to 1. So this is equal to 8 times 1 minus sine of 0, and sine of 0 is 0. So we have 1 minus 0, and so this is equal to 8 times 1, which is equal to 8. And so 8 is the arc length around this entire cardioid represented by r equals 1 plus cosine theta. All right, and so with that, this was the last example for this video. So if you want to see some more examples, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.